All right, continuing on with our CameraUtilities class. In this video, Lee is going to be implementing a very simple method that will calculate a simplified version of our camera's frustum.
Well, not exactly very simple. There is some trig, and some people really hate trig.
Oh, Lee.
But basically, what we're talking about as a simplification of the camera's frustum is if you select on a camera inside of Unity, we get this pyramid that's drawn out. This is the full 3D representation of the camera's frustum. So as you rotate the camera up and down, this whole thing rotates. So left and right, and if I do X, up and down, and if I rotate in Z, we can twist it all around. So we can do all kinds of crazy stuff with it. I don't really care about that. What I wanted to have was another debug tool that allowed me to have a very simple representation of what direction the camera was looking at and the field of view as well as the far clip plane. So just something very quickly that would drop in. So as my terrain patches were drawing in, I could see where they were in relation to where the camera was looking without having to select the camera.
Right.
Because when you're doing a lot of debugging and stuff, it's annoying to have to select the camera all the time. So just having that in there became very useful. So that's what we're going to be doing in this video. Go ahead and jump over. This particular method is going to be called drawFrustum, and I'm going to make this one a private static. It's going to have a return type of void, and draw frust. I always have a hard time spelling this thing. Frustum. See, look, I forgot the T.
Yep.
All right. Okay. It takes no parameters, and then it does a whole bunch of trig. All right. So first off, we need to know where the camera is, but I don't need to know the full camera position because I want to lock this draw frustum to the 0 axis of the world on Y. So we'll make a variable called CP for camera point equals a new vector 3, and we're going to take in our camera dot main dot transform dot position dot x by 0 by this whole thing all over again, but this will be Z this time, or Z for you European folks. And var r. So now we need to figure out basically the angle that we're going to be facing. And for some reason, I kept using R earlier, and I meant A. I don't know why I did that. But this is what happens when you do R&D in the wee early hours of the morning. So I'm going to put these in brackets. What I need to do is get the inverse of our camera dot main dot transform dot rotation dot Euler angles dot y minus our camera dot field of view camera dot main dot field of view divided by 2, and then I'm going to multiply that. Get the right spot. I'm going to multiply this by mathf deg, so degrees to radians, and then I'm going to add basically the equivalent of what pi is 180, so 90 degrees to it. So that will be plus mathf.
Pi is 180?
Yeah. 2 pi is 360.
Oh, you're talking about the conversion. Pi is 3.1415, blah, blah, blah.
Yeah, but when you convert it is 100
converting.
degrees.
I know. I see what you're saying.
This is math.
I was just making sure you weren't losing your mind for a moment.
No, my mind's been gone for a while. But,
I got you.
But in this case, let me go ahead and clean this up a bit so it's easier to be read by our viewers. So basically what this angle is, I can use the same diagram. Imagine this little piece right here is our camera. our frustum. So basically, I'm figuring out the angle from our camera to one point of our frustum, which would be one half of our field of view. So if the camera was facing directly this way, half of our field of view is this way, half of our field of view is this way.
Mm-hmm.
I'm calculating out this first point, then I'm going to calculate out this point, and then I'm going to draw lines that go from the camera's position to this point, from this point to the second point, and then back down to the camera.
Okay.
Or effectively, that's what I'm doing.
Right.
So this just gives us our first angle. Now, just like before, we do var. So like up here where we're calculating that point, we're going to do the same thing. So var x equals mathf dot cosine a. We don't have to multiply by radians in this case.
Our radius?
Or radius,
yeah.
Because I don't care about the distance yet. And then we'll figure out the z point, which will be mathf dot sine, not that sine, the other sine. So Mel Gibson isn't in this one. Bad joke, sorry.
That's
Fail.
okay. You're so funny, Lee.
I try, but I fail miserably all the time. All right, we need to figure out our point 1. So this is going to be equal to new vector 3, x comma 0 comma z. And we're going to normalize it. So we're going to make sure that this is a unit vector. Then I'm going to multiply this by our cameras, our main cameras dot far clip plane. So this will move that point out to where it needs to be in the distance. Then I can do a debug dot draw line, and I will draw the line from the camera's point to the camera point plus P1, because we're doing all of our calculation based off of where the camera is, and this direction is moving. This point in normalized is basically a vector pointing in a direction. It's actually not a point in space. What we're doing by multiplying it by the far clip plane is making sure that that vector that is pointing in a direction has a magnitude equal to the far clip plane. Then we're going to add that direction to wherever our camera is, and that gives us a point relative to our camera of a distance that is the far clip plane away. If you don't understand, just shake your head, hit the I believe button, and believe me, it works. All right, so now we need to figure out the second point. And luckily, it's a lot like the first point. So we're just going to reuse a lot of the same values, except this point will be P2. Instead of subtracting our half of our field of view, we're going to add half of our field of view. Go ahead and clean that up. Now, let's see, this is all the same. This will be all the same. The difference here is we will use point 2. And then once we've done that, we need to draw the last line, which will close off that triangle representing our camera's frustum. So this will be a draw line. We're going to draw a line from CP, camera point plus point 1, to camera point plus point 2. So this will cap off the end of those lines. If I go ahead and build that, make sure there's no arrows. Awesome. Go ahead and say draw our frustum and update. Jump over to Unity. If I hit play, we get a nice triangle that represents where our camera is pointed, regardless of where our camera is. Because if I was selecting our camera, right now our camera is doing all kinds of wonky stuff. And I don't really care what our camera is doing, but I do care that if I rotate my camera, and you're just going to fall forever, aren't you? All right, hold on. Let me see if I can sort that out. Gravity. Hey, gravity equals 0. Okay, so now if I take our main camera and I start spinning it around, will it let me do that? No. Hey, but I can do this. So I forgot I have the full camera control.
Is the end of your...
No, it doesn't match.
Oh,
It's not a perfect relation. I haven't figured that one out yet. Yeah, I saw that, and I have no idea why it doesn't match. Unless for some reason their frustum doesn't exactly match up with the calculations, because as you bring your field of view in,
mm-hmm.
you get closer. But as you get further away, the error gets further off. The only thing I could think of...
Let me ask you this. Hit play again. And this is... The near clip plane has nothing. If you adjust the near clip plane, it wouldn't affect anything, would it?
No.
I mean, it shouldn't.
No, it has no effect. It's not used in the calculation at all.
Right. No, I know. I just... Because it's just kind of odd that you're off
The
like
only
that.
thing that I think could possibly cause it is the normalization part here.
Mm-hmm.
So if I turn this off... But, see, it doesn't really have an effect. So I haven't figured out why that happens.
Interesting. Okay.
Yeah, that's just something that I noticed all along. I wonder if it's... But I've not figured out what happens with that. And I found that when we were doing the camera system for her as well. Even when I was doing the clip plane stuff for determining whether or not the camera was obscure, the calculations didn't work out to be visually exactly the same as the representation that they have in the scene view.
Okay.
And I have no idea why that is. It's slightly off. It's like going, if you look at the angle calculations for the field of view, they're pretty much spot on. But it falls short.
Okay. Interesting.
Yep. But it doesn't, for the purpose of the tool, the purpose of the tool being just to represent what direction that we're facing. I would like to have an accurate distance check, but it's not the end of the world if I don't have that, because it's more important just to know what direction the camera is looking and how much of the field of view I'm looking at.
Okay.
So at some point, maybe when I have time, I'll come back and try to sort that out, but who knows? And it doesn't change with angle either.
Gotcha.
So that'll be our challenge to our members. Anybody can figure that out, send me a PM, let me know.
All right. So is that all you had planned for setting this up?
Yeah, for drawing the frustum, yes.
All right. Fantastic. Well, that will wrap up this video, and that pretty much wraps up the camera utilities for now, doesn't it?
I believe so. I think the next thing that we're going to start diving into is the bundle manager and the bundle assets.
Okay. Sounds good. Well, we shall see you guys in the next video. Thanks a lot.